In this video, we'll go over the answer key for Thursday, April 16th. And what we're talking about here is orbital diagrams. So in our last series of videos, we talked about how orbitals or electron clouds look around atoms, with the P and the S and the D and the F orbitals. Now we're going to figure out, okay, for each atom that we want to look at, what orbitals do they have and what electrons do they have? So I mentioned this on Tuesday, but for each box, for each orbital, we can have 2 electrons in it. And the reason we can only have 2 is because of something called the Pauli exclusion principle. That says that no 2 electrons can have the same 4 quantum numbers. And we talked about 3 of the quantum numbers, N, L, and M sub L. There's actually a 4th called spin. You can be spin up or spin down. And we give those numbers plus 1/2 or minus 1/2. And that's why when we draw one box, we can only put 2 electrons. Because each electron in this box, if they're in the 1s orbital, they have a primary energy level, or N of 1, L of 0, M sub L of 0. The one's pointing up is plus 1/2. The one pointing down is minus 1/2. Now, when we fill up orbitals, there's a pattern to it, and that's called the Offball Principle. And that we always start with the smallest energy levels, and we work our way up. I'll show you how to fill out this chart using our periodic table. There's also called Hund's rule, and that says that when you are putting electrons in a row, you want them to be separate before you pair them up. We can look at the 2p orbital for this. So here at the 2p orbital, we have 4 electrons. Notice that I kept 2 electrons by themselves instead of pairing them up. That's because electrons want to be by themselves. If you remember, electrons are negative. They generally do not want to be near other electrons if they can help it. So they're going to be by themselves before I pair them up. So our first question is looking at the periodic table and determining, can we figure out what the electron configuration is. So I'm going to show you how to do this for C and AS, and I'll put up the answers for the other one. Okay, so we want to do carbon. The way we do this is that these elements are called the S block, and you can just count. Well, I'm getting ahead of myself. So we start with hydrogen. That's the first element in the S block in row 1. So that's 1s1. Helium is the second element in the S block. So even though helium's all the way over here on the periodic table, it's part of the S block. It is the second element in the first row of the S block, so that's 1s2. Now we move down to lithium. S block, second row, first element. So now we're 2s1. Beryllium, second atom, 2s2. Then we move to the P block, so that's 2p1. And finally at carbon, we're at 2p2. So the full electron configuration for carbon is 1s2, 2s2, 2p2. Basically what I just said, you write that down until you hit your element of choice. So let's do that for AS. AS is element 33. So 1s1, 1s2, write that down. 2s1, 2s2, write that down. 2p1, 2, 3, 4, 5, 6, so we can write that down. 3s1, 3s2, so that's 3s2, write that down. 3p1, 2, 3, 4, 5, 6, we're not at AS yet, so we keep on going. 4s2, and here comes the one tricky part with this. For the D block orbitals, even though they're in row 4, their number is 1 minus their row number. So this is actually 3D1. And then we go 3D2, 3, 4, 5, 6, 7, 8, 9, 10. till we get back to the p block, and now we're back to 4. So only D is like that. So 4p, 1, 2, 3. So we are finally done. Now the whole electron configuration for AS then is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. So see if you can follow along and try to do that for our other elements here. Alright, now question 2 is working backwards. Use the electron configuration to find out what element I'm talking about. And the little caveat I threw in here is that when you're doing electron configurations, you can just put in the closest noble gas, or the noble gas that is to the left of you. So what I'm saying here is I have argon in bracket. That means the element we're looking at has the full electron configuration of argon. So we can actually start at argon and then start counting from there. So it's argon, then 4s2, 3d10, 4p6. So that's actually krypton. And let's say our next question would be, what is the electron configuration of Rb, rubidium? We can put bracket krypton 5s1. So by putting a noble gas electron configuration, we are just shorthanding our full electron configuration, saving us some time and having to write down that information. Question 3. What do these numbers mean? So how many electrons are 3s electrons are in Mg? Well, if we go to Mg, we can see it's 3s1, 3s2. Now the number I'm saying after the S, that's electrons. So there are 2 electrons in magnesium. If I were to do nickel, so that's 3d 1, 2, 3, 4, 5, 6, 7, 8. Nickel has 8 electrons. So the number after the letter tells you how many electrons are in that particular orbital. The next thing we are going to talk about are how electrons interact with each other, and that's Coulombs Law. We can ignore this first part, the 1,4 pi epsilon 0. That is basically just telling you how well charged see each other. It's part of Coulombs Law. We can just totally ignore it. All we care about is this second term. Q1, Q2 divided by R. What is the charge of particle 1 multiplied by the charge of particle 2 divided by the distance between 1 and 2? So this tells us the energy of interaction between 2 charged particles if we just look at this part of the equation. And hopefully we get a negative energy. For energy, what I want you to keep in mind is that negative energies are favorable, positive energies are unfavorable. So if you get a negative energy, that's good. If you get a positive energy, that's bad. So this question just deals with looking at Coulombs Law and says which one's the lowest or the most negative. So the way to do this without having to do any calculations is first just look at the charges. Even though I was circling distances there. So we have a +1 and a -1. That's good. Opposites attract. Remember, we want a negative number, so a positive times a negative will give us a negative. Positive times negative, good. Positive times a positive. We can immediately cancel out C. If I multiply a +1 charge, say that's Q1, and this is Q2, I get a positive number. That's not favorable. So C is eliminated. Then D. +1 and -1. Alright, now we have C eliminated. Let's look at the distance. The closer 2 particles are, the more favorable it is. So A and B both have a distance of 100. D has a distance of 200. So D is probably not going to be the strongest. So I'm going to eliminate D. Now I just have to check between A and B. So B has a +2 charge and a -1. A has a +1 and a -1. So B has bigger overall charges, then that's more favorable. So the answer to this is B. The last thing we're going to talk about for this problem set is the idea between valence electrons and core electrons. So in chemistry, only the valence electrons really do any interactions, any chemical processes, or any chemical reactions. Core electrons do not. And the difference between core and valence is this primary energy number. So if we look at fluorine, which is 1s2, 2s2, 2p5, you'll notice the highest energy level here is 2. And when I'm counting valence electrons, that's what I care about. So how many electrons are in the highest energy level? Well, we have 2 plus 5 equals 7. And a core electron is any electron that's not in our highest energy level. So here we have 1s2. So we have 2 electrons that are core electrons. So how many valence electrons are there for these elements? I'll do oxygen for you. So oxygen, the full electron configuration of oxygen is 1s2, 2s2, 3p4. Or sorry, 2p4. So our highest energy level is 2. And we have 2s2, so that's 2, plus 2p4, which is 4, for a total of 6. And the number of core electrons, 1s2, would be 2. And that is it for this video. I will see you in the next video.